Alright, hello everybody. This is chapter 1.1, graphing polynomial functions. We're going to start off with the vocabulary. First of all, we're going to define a set. A set is simply a collection of objects. Let me pause real quick. There we go. It's a collection of objects. Just want to get a little bit better handwriting on there. Basically, and what we mean by objects are just numbers. So the way we write that is we'll put a little curly brace, and any number that's in our collection, like the number -2, if 0's in there, let's say 7's in there, and just for the fun of it, 372. It's just a collection of objects. That is a set. That's one set. Now, a set might be a range of things. Like a set could be the set of all x's that are greater than 0. All right. Basically, this is set builder notation. We'll talk about it a little bit later. But basically, what this means is all x's such that are greater than 0 is what that means. And we'll talk about it more later if it doesn't make any sense at the moment. But we'll get to it. A subset is when all wow, that's spelled correctly. W-H-E-N, all members of a set are also members of another set. It's kind of like saying a subset is basically saying women are a subset of the human race. All women are humans, but not all humans are women. Same idea here. If I have the set 2, 3, and 4 is a subset of the set 2, 3, 3.7, 4, 9, 12, 72. All right. This first one is a subset of the second one because all three of those are contained in the other one. All right, the collections of objects, the set I did earlier, the ones from up top, these ones, this is not a subset of that because this is when x is greater than 0. Well, this -2 is not greater than 0, so therefore this one is not contained in there. Okay, so that's an example and a counterexample. But basically a subset is when everything is contained in a larger set. All right, pause, I'm going to move on to the next one. All right, endpoints. Now this should be a review from geometry for you. Endpoint is points, O-I-N-T-S, that represent the end of a line segment or ray. The end of a line segment or ray. All right. And again, that's straight out of geometry. So if I've got point A and point B in this case are both endpoints because they're both at the end of this line. Whereas point C and point D, which I'm drawing right now, this is a ray, if you recall. All right? Only this is an endpoint. This one is not the end of the line, so it is not an endpoint. All right, so hopefully that's self-explanatory. That should be a bit of review. A bounded interval is an interval that has a finite length. Is an interval with a finite, F-I-N-I-T-E, length, L-E-N-G-T-H. My wife is correcting me on something. I'm saying line segment on there. Okay, never mind. Everything's good. Bounded interval is an interval with a finite length. For example, this example, A to B, has a finite length. And basically, finite means it stops. There is an end to it. All right? So, for example, if you're on a graph and you got, -1, 0, 1, and 2, and 3, a finite would have endpoints. All right, it doesn't go on forever. It stops. Whereas non-bounded interval, which we'll talk about in a second, doesn't have an endpoint. All right, it may have one, but at least has one thing that goes on to infinity. So, like this one up here, that is an unbounded interval. Okay, so really, basically, we just define unbounded interval. And interval that has infinite length. L-E-N-G-T-H. Almost forgot how to spell length. Or you can think of it as something that is not finite. Something that is not finite is infinite. So, for example, earlier, that ray over there, from C to D. All right, this ray is infinite. It is unbounded. So the way we're going to see this in graph in Algebra 2 is, again, in the form of a number line. So like -1, 0, 1, 2, 3. If I have a graph that starts here at 1 and goes to the right forever, remember we fill in the arrow to show it's going on forever. All right, that is unbounded because it goes on up forever. As high as you can count and even higher. Okay? Alright, last word. Let's pause and get to it. Alright, last but not least, set builder notation. Set builder notation is a way to write an interval using symbols to define a set. Alright, so basically it's just a way of using symbols, but the formal definition would be a way to use symbols, S-Y-M-B-O-L-S, to define a set in terms of the set's properties. P-R-O, let me spell that a little easier. P-R-O-P-E-R-T-I-E-S. Alright, and here's basically what I mean by this. What we showed you earlier was I showed you something that looked kind of like this. We gave a little squiggly line, x. So basically this is the set of all numbers x such that x is less than 8. Not s, 8. Okay, so basically here's how we read this. It would be the set of all real numbers. Basically, that's what this part is. Okay? Such that, that's what this line here in the middle means. Okay, so it's the set of all real numbers x, put an x in there, such that x is less than 8. And that's where that last argument comes in. Alright? X is less than 8. And that is that piece right here. Okay? So what we just wrote there is the set of all numbers x such that x is less than 8. If I wanted to use that one earlier, that unbounded interval, where I went from 1 to 4 or something like that, we can write that one real quick. This would be the set of all real numbers x such that x is greater than 1 but less than or equal to 4. Alright, so basically how you read the inequality, just so remember, if you're on the bigger side, that means you're bigger. If you're on the smaller side, that means you're smaller. Alright, so x is bigger than 1, but it's smaller than 4. So basically what this is saying is x, the set of all real numbers x, such that x is between 1 and 4 included. And the way you read that is 1 less than or equal to x less than or equal to 4. But it basically means x is between 1 and 4. Alright? And there you go.